Okay, welcome back. So today we're going to talk about power. And we've been talking about energy up to this point, and that really is a very convenient way of discussing what's going on in the circuit or any kind of dynamical system. But oftentimes we want to know how fast that energy is used. And if you remember from your mechanics classes, the energy per second, the energy being used per second, the amount of work being done per second, the energy being given per second, all of those are equal to the power. And it'll either be the power radiated or the power absorbed, but one way or another, it's about the energy per unit time that's coming in here. So we have discussed up to this point how the energy is moving, but now we want to talk about maybe how long I can produce that energy. And this is one of the key aspects when we're talking about batteries. Most batteries are rated in amp hours or milliamp hours often. And believe it or not, it sounds like, oh, well, that's got something to do with time, but that's actually just a unit of charge. Remember that an amp is a coulomb per second. And if I multiply by time, hours, so I've got a factor of 3,600 in there. But if I multiply by time, the time units cancel and I'm just left with coulombs. So the amp hours that are written on your battery is literally how much charge is stored in them. However, we can use the concept of power to find out how long that battery is actually going to last under a given load. So that's what we're going to work out now. So go ahead and get that section out of your book and let's get started. Okay, so take a look at the books under power. And let's see if, first of all, if we can come up with a definition for power. And we're getting up there at the top. You can see what we're doing here. But we define to be the power to be the amount of energy used in a certain amount of time. And so if you were talking about average quantities, we typically use the letter P for power. And that would be the change in energy, whatever kind, electrical energy is what we're talking about at this point, in a certain amount of time. However, we want to not have to use an average. We want to be able to use our instantaneous power. What is the power at that given second, at that given instant from there? Well, if you remember back from your mechanics courses, that's really easy. We just change that to be a differential instead of the delta. So du dt. So this is how my power is defined in any general case. You take how much energy you have, the derivative of that with respect to time then is going to give me the power. So let's solve that. And so look at microtask 1 down at the bottom here. It says you want to find an expression for power in terms of the current and the electric potential. So this is going to be one of the most basic forms of power. What we have here is great. It works, but let's apply it to something. Now, I need the energy. So how can I write the energy in terms of the current? And the voltage, for that matter. So think about it. I know that UE is equal to Q times the voltage. And if you don't remember that, go all the way back to your early notes and see if you can remind yourself from that. Hopefully this is in your flipbook. You should be going through your flipbook and be able to find these things very quickly. But the potential energy is the charge times the electric potential. That's how we define the electric potential. So I'm going to put that back in here. So I get dQV dt is equal to the power. All right. Now, I need to know, how does the charge depend upon time? Well, now the voltage here, it's going to be in our circuit. We're going to have it be constant, so we can pull that out. So V times dQ dt must equal power. Well, if you remember, dQ dt is the definition of the current. So that is the current. It's the instantaneous current at any moment, which is what we're looking for with this. So putting that all together, I get a really simple result. And we generally write that with the I first, just for tradition, but you can do whatever you want. It's going to be the same. So the power is going to be the current times the voltage. So that should be a very easy to remember expression for that. Now, we can get a couple of other useful forms by applying Ohm's law. So to start off with, if you look in the book, we want to substitute for the voltage. So the voltage is IR from Ohm's law. That is the root form of Ohm's law. So I'm going to plug that in here. And so I get P is equal to I times IR, which is just I squared R. So there's another useful form. And oftentimes you'll see that written as P I squared R. You do it whatever order you want to do it in. Okay. Now let's get it in terms of the voltage and the resistance. So I want to get rid of the current. Here we got rid of the voltage. Now let's get rid of the current. So I'm going to move this over here, and V over R equals I, and I'll put that back in our original expression. And so I get P is equal to V over R times V. And so therefore, P must equal V squared over R. So all three of these forms are very useful, and you should be making a flipbook page that has each one of them. Which one you use, well, it just depends on what you have and what you want. So you'll find that you can use any of these. If I have the voltage, well, then I'm probably also going to use either this form or this form. Many times I have the voltage and I have the resistance. So great, that's the one that I want. So just look at the situation, analyze it, and then it will immediately just pretty much tell you which form that you want. Okay, so we talked about how batteries are rated in amp hours. What we want to know is how long will they run? So I'm going to scroll this up and give myself a new page here. So down at the bottom, we've got a fairly simple expression. The runtime, how long your batteries will work, must equal how much charge is stored in them divided by the current. So how much charge per second we're using. See if that makes sense, right? So I want to know how much, first of all, I would need to know how much charge is stored. Well, that's going to be in amp hours. And I need to know the current. And so from the current, then I'm going to get that from the power. All right, so let's take a look at the first scenario. So in the first scenario, I've got my microcontroller, my main board, and then I've got some battery here. Right, so here's my load. This is my microcontroller. And then this is the battery that's being provided for that. And we tell you that the battery is rated for 1.5 amp hours. That's how that's written. Amp times hours. I'm sorry, 1.8 amp hours. And the voltage is going to be 5 volts because that's what our microcontrollers all need. So they're going to have to be connected to a 5 volt source. And what I want to know is, what is the runtime? All right, well, for starters, I've got the storage. But I also need to know something else. I need to know the power. And that's given in the problem statement here. So the power used is going to be 0.4 watts. And the watt is the unit of power. And yes, James Watt is one of my ancestors. So the unit watt is named for James Watt, who is the inventor of the steam engine, one of the early sources of power that was out there. So a watt is simply a joule per second. I'm just a joule every second, but you need that already, right? So this is energy, joules is energy divided by time, okay? So if you have a 100 watt light bulb, it's using 100 joules of energy every second. Simple as that. Okay, so how are we going to set this up? So I know that P is equal to this. I know that my voltage is equal to, go ahead and write that as 5 volts. And I know that my storage, which I don't really have a letter for, so we'll spell that out. So I know that my storage is 1.8 amp hours. What I'm missing here is the current, as we said. So let's use the power to get the current. Question is, which expression do I want to use? And again, like I said, you want to look at what you have, and then that will tell you what you need. So here, I don't have the resistance, but I do have the voltage. So I'm going to use this form, and I'm going to solve this for the current. And you see why I chose that, because I have the power and I have the voltage, and what I want is the current. So the current is going to equal to simply the power divided by the voltage. So we're going to put that in our runtime. Here's where it's very important that you keep up with your units, because amp hours are obviously not an SI unit. That's not something that you're going to have as a standard. So our storage is, we'll just call that S. Let's use a symbol S for that because I'm too lazy to write out storage. And then divided by P over V is the current. So I'm going to simplify that. And so the storage times the voltage divided by the power determines how long this is going to run. So let's put that in then. I have 1.8 amp hours times 5 volts divided by, now this is 0.4 watts, and a watt is a joule per second, so be very careful with that. So this is watts. And so now all I have to do to divide that out is I want to just simply do the math, and well, I've got it written out here, and I get 135 hours. So make sure that that makes sense to you. So a watt is going to be my amps times my voltage. So remember that this is watts, this is amps, and this is volts. So an amp times the volts must give me the watts, and it just leaves the hours. So that's a pretty convenient way of doing this. So that battery then can power that main board for 135 hours. That's a nice long time. And this is actually fairly typical numbers for the types of batteries that we're going to use. They'll power that main board for a very long time. All right, so let's look at scenario 2. Now, this one is probably a more typical use case. I'm pretty rarely just going to have my main board sitting there being fat, dumb, and happy. I usually want it to do something. One of the most fundamental things to do for a robot is to make it move. So let's put some motors on here. All right, so let's draw our robots here. And so we're going to have a motor here and a motor here. And we'll connect those to the main board like so. And this is our main board. And then they will be connected to a battery. In the case of the main board, that's going to be a 5 volts, since all of our main boards run on 5 volts of potential. Now, before we get going though, ask yourself, are those motors in series or are they in parallel? And how do you know? Well, they're in parallel, and the way you can think about that is because as the current comes in, so this is my negative electrons coming through here, it's going to split. My current is coming this way, it's going to split. So if it splits, by definition, they're in parallel. But you want that, because if they were in series, maybe something like this, right? So if these are my motors, if this one is off, then this one is off. It would be impossible to run this motor without this motor also being there. So that means your robot can basically just go forward, and that's not what we want. So this way, if the top motor, for example, is getting power, we can have the bottom motor off, and then that will make my robot turn this way. So having them wired in parallel makes a big difference with this. All right. So now what we want to do is let's look at scenario 2, and we want to find the runtime for the robot's motors, and we want to know what is the current through the main board, because our main board is limited to 40 milliamps of current. So 40 times 10 to the minus 3 amps. So let's go through the same procedure that we're going through before. Now let's label all our parts here. The main board power is 0.4 watts, we said. And then it tells you that each one of these motors is 10 watts from there. Okay. So let's go back to black and let's figure it out. Now, if we want the runtime, remember that the runtime is equal to the storage divided by the current. Well, we're going to use the same 6 AA batteries. And so that's going to be 6 times 1.8 amp hours of storage. And if you multiply that out, then we're going to get something like 10.8 amp hours total. But I need to know the current. And so just like we did before, we're going to use the power equation. And I need to find out which one I'm going to use. I want the current, I know the voltage, and I know the power. So the right one to use for that then is going to P equals IV, just like that. So we're going to solve that for I, and I get P over V. All right, now the battery here and the main board are having to provide both of these, power for both of the motors and for the main board itself. So our total power here is actually 20.4 watts. Make sure you understand why that's true. It's still going to be 5 volts. And so when you divide that out then, just punch it into your calculator right quick. And when I did this, I got 4.08 amps. So that's my current. So now I'm going to put this into my runtime equation here, and I've got 10.8 amp hours divided by 4.08 amps. And you see the amps cancel and leave me with the hours. And when I did that, I got 2.6 hours. So that's the runtime. So you see that while we got well over 100 hours with just the main board, when I put those motors on, that time that the battery will run drops dramatically. Now I'm down to just two and a half hours roughly for that. But there's a bigger problem. So the current draw right now is 4.08 amps. And remember that our main board can't handle any more than 20 milliamps. So that's going to be a problem. Your motor's going to brown out, or your main board's going to brown out, or worse, it's going to fry. And so that's simply not going to do what we need it to do. So the question asks, how do we actually do this is we put a driver board in here. And so then the driver is on a completely separate circuit that is responsible for managing the motors, providing power to those motors, so that the main board, all it has to do is just send a little 5-volt on signal, just like you would do with an LED, and say, hey, turn the motors on. And when it wants them off, it turns them off. We can control how much that is, how speed we get from that by controlling how long we keep the motors on and off with that. But either way, the voltage that's required isn't going to be provided by this battery pack. We're going to have a separate battery pack for that. So let's see what we can do. Let's go on to scenario 3 then. And this is probably a more realistic layout. So we're going to have the motor, and then we're going to have a driver board right here. And then the second motor. And it also has an independent driver board. And these two things are completely independent of each other. And they need to be, right? Because we want to control each motor individually. Now the connection to the main board is nothing more than a logic connection. So all it's going to do is it's going to turn the driver boards on and off with just an on or off signal. It's not going to try to drive the motors from that. So over here then we've still got our same battery pack that's providing 5 volts, but now I'm going to have a separate battery pack that's going to drive both of these drivers, and that's going to be a key thing. So we'll just draw it this way. So this battery pack then, we don't know what it is offhand, what it needs to be, but this battery pack is going to drive both motors. So even though each circuit is independent, we're using the same board to drive them. That's going to be important here in just a second. All right, so let's figure out how much voltage that we're going to need for this. So we're going to start the same way that we've done before, but right now then, all I need to worry about is this part of the circuit. I don't actually care what's going on with the main board side because it's got its own battery pack. The battery pack that we're going to use here, what we typically use in lab, is actually the same one that we use here. So that's going to be 6 times AA batteries. So that's going to provide a maximum. Remember, each AA battery is 1.5 volts. So the maximum voltage we can apply here is going to be 9 volts. And then the storage is still going to be 6 times 1.8 amp hours, or 10.8 amp hours. So that's going to be the same. And typically we literally use the same battery packs. We just stack them on top of each other. So I've got 2 independent battery packs controlling this. Okay, so let's see about getting started here then. So first thing we need to do is we need to figure out what is the voltage that's going to be needed here. So the voltage, we could just use our P equals IV equation, but we're going to solve it for the voltage this time. So that's P over I. Now, what is the current going through? In this case, we actually tell you the current. So we tell you that the current going through each individual driver board is 1.2, let's see, I forgot, is it amps or milliamps? 1.2 amps, right? So it's 1.2 amps. And then this driver board also has 1.2 amps. Now, the battery pack, though, has to provide the current for each one of these to power it. So for the 10 watts, so for each one, we're going to have 10 watts, and I'm going to have 1.2 amps. And remember that the voltage in each driver has to be the same. There's no other way around that, right? Because voltage is just a potential difference. That's it. And it's all being provided by this battery right here. So that's going to be the voltage of my battery pack. And so when I do that, I get 8.3 volts. Check and make sure that you get the same thing. And so this is going to be 10 watts divided by 1.2 amps, and we get 8.3 volts, which is less than our 9 volts. So that's good. We're good to go for that. Now, to find the runtime, however, both of these driver boards are depleting the battery. So they're both going to have to be considered in there. And that's a little tricky. That's you, the engineer, you, the physicist, have to think about what's actually going on. Don't just take an equation and plug in numbers and call it good. You're not going to get the right answer. So we're going to take our runtime then. The runtime is going to be the storage, which remember is all we have available to both motors. And then we're going to divide that by the current. But it's got current is charge. Current is moving charge. And it's got to provide charge to both of these motors. So that means I'm going to need 2.4 amps of current total. So, and that's because it's in parallel rather than being in series. Let's get the camera back. There we go. So we've got 10.8 amp hours. And we're going to divide that by 2.4 amps. Again, my amps cancel. I'm left with hours. And when I do that, I get a runtime of 4.5 hours, which is pretty reasonable. So with that, we can run on that battery pack for a fairly long time, as long as the batteries are fresh. Okay, so the key here, though, that you have to remember is that these two circuits are independent. But then also we have to think about the fact that I'm trying to power two other circuits. Let me just outline them both. Two other circuits from the same battery pack. And so that kind of complicates things a little bit from what you might be, thinking of just plugging in numbers. But if you think about what's going on physically, then it should all make sense. Okay, so this is a short lesson, but an important one, because as we talked about, a lot of the design here, you've got to think about what is my robot or whatever application I'm doing, what is it going to need? And then I have to provide the power so that it can do that job for a long period of time. I need just having enough energy to do it for a second isn't really worthwhile. I've got to be able to do it on the order of hours. And so that's going to determine how many of these batteries I need, what their voltages need to be. And so that's what I would wire in series. And all of these considerations go in. And then once I've got my system designed, I can do these calculations to find out what that runtime actually is. So it's good practice for the real world. If you guys, as always, if you have any questions, just make a discussion post and we'll see if we can get them answered and worked out there. All right. We'll see you next time.